Imagine this cascade of data. Every day, modern enterprise systems are flooded with millions of raw, unorganized points of information. Finding the value in this mountain of noise happens during the Knowledge Discovery in Databases process, or KDD. Data mining is the critical fifth step in that cycle, the moment where we actually apply algorithms to the raw records. But before writing any code, analysts face a definitive choice. Do you use this data to predict a specific future event or to map out hidden structures that exist in your business right now? The stakes are high. Choosing the wrong algorithmic path doesn't just waste massive amounts of computing power, it generates statistical noise that can lead a company toward a flawed strategy. Ultimately, a data mining algorithm is only effective if its underlying logic matches the specific business objective you need to achieve. To solve that problem, we rely on two distinct architectures: classification and clustering. Classification is the predictive path. It is built to forecast specific, known outcomes, like determining if a transaction should be flagged as fraud. Clustering takes a descriptive approach. It explores the data to uncover unknown relationships and affinities without any predefined labels. The decision hinges on your input data. You have to check your historical records. Has a human already manually labeled this information, or are you looking at raw, untouched data? It also depends on the business question. Are you trying to forecast a specific category, or are you trying to explore a new segment? The final choice between these architectures depends on whether the business goal requires predicting the known or discovering the unknown. Let's look at classification. This is a supervised learning mechanism that builds a mathematical, rule-based decision model. To work, the system must be fed highly structured training datasets before it can generate any insights. Crucially, every single record in that training set must have a known, predefined label. The machine needs to see thousands of examples of successful or failed outcomes before it can learn the difference. The primary trade-off is the human cost. Generating these labeled datasets requires massive amounts of time and effort to ensure the training data is accurate. Engineers then apply algorithms like decision trees, naive Bayes, or support vector machines to the data. This shows how the math works. The algorithm learns the structural boundaries from your labeled data, creating a mathematical line that separates the different categories. When new, unseen data enters the system, the model checks which side of that boundary it falls on, assigning the correct label automatically. This results in high-speed sorting for tasks like spam filtering or bank loan approvals. However, this model is mathematically rigid. It is blind to any novel patterns that fall outside the categories it was explicitly trained to recognize. Classification provides predictive certainty, but only if you are willing to pay the high upfront cost of human data preparation. Clustering uses a different architectural approach. This is an unsupervised learning mechanism designed to process massive pools of raw, unlabeled data. The logistical advantage is clear. You don't need humans to manually label thousands of records to get started. Instead of following predefined rules, the algorithm measures the mathematical distance between raw data points to find natural affinities. This scatterplot shows the logic in action. First, it maximizes intra-cluster similarity, which forces similar items together into tight groups. Then, it maximizes inter-cluster variance to push these distinct groups as far away from each other as possible. For this type of exploratory analysis, we rely on algorithms like k-means, Agnes, or dbScan. These systems can reveal hidden structures and behavioral groupings that would be impossible for a human to spot in a standard spreadsheet. However, analysts must be careful of the curse of dimensionality. Feeding the machine too many irrelevant attributes makes the data points too sparse, leading the algorithm to find accidental correlations rather than useful insights. There is also a major interpretation cost. The machine can group the data perfectly, but it has no understanding of what those groups actually represent in the real world. By skipping the manual labeling phase, clustering reduces the labor required for data ingestion, but it shifts that workload to the backend, where human interpretation and domain expertise become the primary requirements. The choice comes down to where you want to spend your resources. Predictability requires upfront data preparation. Discovery requires backend human analysis. This framework allows you to select the right algorithm based on your specific business situation. Take a fraud analyst at a major bank. They have years of historical logs showing exactly which transactions were flagged as high risk. Since the problem is binary, legitimate or fraudulent, and the categories are well defined, a predictive model is required to automate the decision. Now, consider a marketing strategist launching a new product. They have a massive user base, but no idea how people will actually use the new features. Because the market segments are unknown, an exploratory model is necessary to discover how users are naturally grouping themselves. Success doesn't come from picking the most advanced math. It comes from picking the architecture that mirrors your data constraints and your business goals. The most effective data science pipelines don't actually isolate these algorithms. Instead, they sequence them. Oncology researchers often use clustering first to process raw genomic data and identify entirely new genetic tumor profiles. They then take those newly identified profiles and feed them into a classification model to accurately predict which treatments will work best for new patients. Organizations reach full maturity in KDD when they stop treating these as isolated choices and start sequencing them to turn statistical noise into actionable patterns.